In this presentation, I'll discuss and analyze the biomechanics of a soccer goal kick, a pivotal skill that provides strategic advantages in game conditions when executed consistently. Effective goal kicks allow for faster switches of possession and opens up direct attacking opportunities, improving the team's passing affordances. By further investigating the execution of this closed skill, biomechanical principles that are present can be established and conclusions can be drawn. By conducting this biomechanical analysis, we will identify key principles that influence both performance and injury prevention. The generation and transfer of force during the kick is crucial for achieving power and precision during the skill execution. Biomechanical factors such as knee stability, core engagement, and foot-to-ball contact are integral to this process, directly impacting the quality of the kick and its potential for injury reduction. A comprehensive training approach that combines proper technique, individualized training, and targeted conditioning is the most effective to see critical growth. When athletes apply biomechanical principles effectively, they can enhance their performance while reducing the strain and risk of injury, contributing more in terms of skill execution success and injury prevention from optimized technique modifications. The biomechanical goal of a soccer kick is to maximize both ball speed and accuracy by optimizing the force generation and ensuring precise directional control. To achieve this, the following phases are critical. The approach phase builds momentum and sets up the proper alignment for the kick, preparing the body for the upcoming movement. The backswing. During the backswing phase, the leg is prepared for forceful forward motion, storing energy that will be transferred through the ball. During the forward swing, the kicking leg generates speed and power, resulting in a powerful strike. During the follow-through phase, the energy transfer is completed, ensuring a deceleration of the kicking leg to reduce the risk of injury. Research by Numome highlights that the use of the dominant or preferred foot increases the speed and execution of the total kick and raises the newtons of force generated as opposed to the weaker foot by what was found to be about 26 newtons of force. Our participant, being right-footed, performed the kick with the dominant leg, which aligns with these findings as there was no involvement of the weaker foot during the trial. A deterministic model outlines the key phases and factors that determine the effectiveness of a soccer goal kick, breaking the movement into 4 crucial phases: approach, backswing, forward swing, and follow-through. The force generation is achieved through controlled angular velocity and knee stability. The backswing and follow-through phases are crucial for generating speed, with angular velocity accelerating the leg to generate the ball speed. Knee stability ensures the proper alignment and reduces the risk of joint strain. The balance and core stability. Core stability ensures smooth energy transfer, preventing strain on the lower back and limbs. Trunk rotation in both the pre-kick and contact phases optimizes the power generation and control. 2 qualitative features: knee stability and alignment, and core engagement and trunk rotation. Knee stability and alignment. Proper knee alignment during the planting phases minimizes the lateral strain and directs the force efficiently to the ball, enhancing joint stability and performance. Core engagement and trunk rotation. Core engagement aids in balance, and trunk rotation generates rotational power, enhancing the ball speed while minimizing the lower back strain. Quantitative features. Angular velocity of the kicking leg. A faster kicking leg is linked with increased ball speed, essential for powerful strides. Foot-to-ball contact force. Maximizing the contact force ensures the efficient energy transfer, enhancing the power and accuracy of kicks. This is according to Rommers and Rossler, 2021. To ensure effective data collection during the recording of the trial footage, several preparatory steps were taken. Firstly, the setting was carefully selected on the football field with optimal lighting conditions, where light illuminated the participant from the front, enhancing the marker visibility. The cameras used were iPhone 11 models set 120 frames per second, with a standard lens to avoid the wide lens distortion when analyzed in the Canovia software. This high frame rate allowed for accurate freeze-frame analysis to track the angles of the kicking leg across the 4 movement phases when defined in the deterministic model. The setup also included a mostly white background to improve the marker contrast, and the participant wore tight clothing to ensure clear visualization of critical movement features. Markers were placed on the key points: the hip, the knee, the ankle, and the foot, after the participant completed a brief 3-minute warm-up with the ball. The participant was instructed to perform a high-level goal kick while also helping calibrate the materials by holding rulers and other calibration material. Filming was conducted with 2 cameras positioned 5 meters away from the right-hand side and behind, one capturing the rear view and the other from the right-hand side. Although the high-contrast markers provided visibility on the participant, they did shift slightly and one fell off during the force generation of the kick. This might be one consideration for further testing. During the data collection period, we focused on both qualitative and quantitative observations. Quantitatively, we analyzed the angular velocity of the kicking leg and the total load arc angle, using the high-speed footage to calculate these values later. Qualitatively, we assess the knee stability and the trunk rotation of the athlete to identify any deviations that might affect the kick's effectiveness. Based on our analysis, here's how the variables performed. The quantitative data shows that the higher angular performance velocity resulted in a faster foot speed, which translated to a greater ball speed, a key performance factor. However, the slight instability in knee alignment during the backswing indicated a potential inefficiency in force transfer and a risk of knee strain. The qualitative analysis revealed a limited trunk rotation in some kicks, suggesting a missed opportunity in the full power generation. By optimizing these variables of kick movements, can yield better performance and help prevent injuries. During the data collection and analysis variables, a slight valgus position in the knee limiting stability and insufficient trunk power generation was noticed. Minimal use of momentum to generate the maximal force with the same level of accuracy was also noted, and a visible knee angle instability in the footage attempts highlights the inconsistent foot placement angle of the off foot. The example on screen should show 33 degrees of forward leg follow-through between the ankles and the hips. A lack of hip thrust velocity was seen, as per Ronger's 2021, reported on the hip usage in power generation of the kick. The subsequent minimal rotation and summation of forces led to balance countermeasures, a weaker bent knee and more affordances in movement due to the lack of game-like environment. A submaximal performance was noted by performance indicators. The other suggested biomechanical corrections could be considered the ACL swelling or associated muscles that within that knee bracing region due to the improper trunk rotation, which could strain the knee when under rotation under a high amount of repetitions. So for someone that's training for a high period of time and not knowing what tendons they might be straining. Addressing these faults could improve performance and make their technique safer for the athlete long term. For knee alignment, it's recommended that targeted strength training to reinforce the knee stability and alignment, such as hip and core exercises. For trunk rotation, rotational core exercises and drills focusing on full kinetic chain engagement can enhance the rotational power. These adjustments align with the evidence-based recommendations for enhancing both power and safety in soccer kick mechanisms. In summary, the biomechanical analysis of the soccer goal kick reveals critical insights for improving performance and minimizing injury risks. Focusing on knee stability, trunk rotation, and the angular velocity and the contact force allows us to refine technique and optimize the kick using virtual technology. This analysis not only highlights the technical improvements that can be seen in the athlete through training, but can also demonstrate the value of biomechanics in the real-world sports application setting. I spoke with a participant and he thought that he needed to find the optimal strike location on the ball, so thinking about the moment of impact, and that may have affected his follow-through. So those innate internal focuses of attention might have also been at play.